Hello, everybody. Welcome to STA 513, Video 6. So let's go ahead and get to the main area topics today. Today, we're going to move into the materials that will be part of the second exam, where we start giving the introduction to two-way ANOVA. Now, you may have gotten an introduction to it last spring with STA 512 or wherever you guys took the STA 512. Like with the one-way ANOVA, we want to blow this up into considering a lot of issues that we talked about in one-way ANOVA, namely things like confidence intervals, contrast, power, and building off of things we constructed in the one-way ANOVA and extending them to the two-way ANOVA model. As a simple extension, what we have going on is, namely, in a two-way ANOVA, we have two factors or two predictors. In one of the depression studies we've talked about before, this DeRubis-Holland study, the two factors that happened to be involved in that study were site, in which the treatment study was conducted at two sites, the University of Pennsylvania and Vanderbilt University, and three treatment arms, where people got medication, placebo, and cognitive behavioral therapy. So in this two-way layout, we in essence have 6 cells. And with the 6 cells, we have 6 cell means that we're trying to estimate. In this example here, the mu11, this would happen to correspond to the mean, the true mean for site 1, we'll call that pen, treatment 1 medication. Similarly, mu22 would be the treatment mean, the true mean for treatment for site 2, Vanderbilt, and treatment 2, placebo. Now, when we were talking about the one-way ANOVA model, the null hypothesis focused on, namely, the equality of these 6 cells. That's not what the two-way ANOVA is doing. The two-way ANOVA, when we're in this model of assessing interactions, really is aimed towards answering whether or not the treatment effect, or in this case, or the side effect, depending on which factor you want to talk about, whether or not we'll talk about in terms of the site effect or site differences, whether or not the site differences vary across the 3 treatment arms. So the interaction model, I would think of it more like this, and this is really where we want our main focus on this one to be is to, let me get to the equation, let me put this one here, is really this. Oops, don't want that there. I'll put this here. So it's really, this is what we're really after. I might want to exaggerate this. Let me go here. Whoops. Let me go here. I think we're going to steal this symbol. I think one more down, one more up. We'll steal this one here. And then let me just borrow this as we go across. This is really what we're going after in the two-way ANOVA. It's really answering this null, whether or not the difference between the 2 sites varies across the 3 treatment arms. So in English, the null is that there is no difference in the site differences across the 3 treatment arms. That's the null hypothesis. that's really what the two-way ANOVA model is getting after, is trying to answer. It's really not whether or not the two factors have an interactive effect. Interactive effect means that they depend on each other, that there's some kind of dependence, interrelationship that we would need to really focus on in communicating the results of what we have going on. So that's really what we want to really focus in on as we begin this two-way ANOVA layout. Now, Chapter 19 starts us out with a two-factor study where we're going to assume that the cell sizes in this case, in the 6 cells, and again, a cell I'm thinking of as are the group of data coming from level I of factor A. So this is level 1 of site, and level J of factor 2. And this is level 1 of treatment. So there are 6 cells that we're really focusing in the communication. So now, in this example, or Chapter 19, really says, unlike what we saw with the Kenton data, where we had the 5, 5, 4, 5 for the store designs, for the cases design, in this chapter, we're going to focus on the situations where we have equal size per cell. When we get to Chapter 23, we're going to remove that restriction. And in reality, that restriction does nothing for us unless we were deriving things by hand, but we're not. We're letting the software do it for us, so whether or not it's SAS, whether or not it's R, whether or not it's STA, whether or not it's SPSS, we're letting the software do the work for us. But namely, we have 2 categorical explanatory variables in our model. Now, the models could be experimental, could be observational, or a combination of the 2. What we just saw in the example we were just looking at is we have one observational factor, the site. We observe the site the patients are coming from, and we have one experimental factor where the patients are randomized to one of the 3 treatment arms, treatment assignments. We call it the treatment assignment an arm of the study. So that's what we have there as we move on. So this is called a two-way ANOVA because we have 2 terms in the model. And this begins what I call part 2 of the course. Well, with the 2 terms of the model, just got to keep in mind that the mathematical symbology gets a little additional complexity. In this case here, we let the IJK subscript represent the kth observation in the IJ cell. So that means we have the kth observation in level I for factor A and level J for factor B. And again, the number of levels for each factor can be whatever they are. In the example, we were just looking at 2 levels for site, 3 levels for treatment. As we said in Chapter 19, it assumes the number of observations in each cell is the same. Chapter 23 relaxes that restriction. And in a lot of my research, I've seen this a lot, where we have these multiple factors. And the one study by Hedeker and Gibbons, those guys are eventually enrolled to the longitudinal class. We talk about Hedeker and Gibbons, which lay out an introduction to longitudinal data analysis. They do this approach where they on this big, really the biggest treatment depression study involving psychotherapy versus medication. This treatment they call TDCRP study. And in this study, they were interested in whether or not treatment completion, whether or not people complete the whole longevity of the treatment study, whether or not that impacted the treatment response. So in this study by Hedeker and Gibbons, we're interested in the completion, yes, no, interacting with the treatment assignment, which happened to be 4 treatment arms in that study. In the cocaine addiction study that you guys will see a lot of, in this one, we were looking to see whether or not the treatment effect depended on gender. Whether or not which treatment did best depended on gender. And if you think about this, that issue is really important, because if we have one treatment that is highly effective, but we see that treatment effectiveness depends on gender, part of that story, or one story could be, is the treatment's highly effective in men, but the treatment has no impact in women. That interaction relationship is saying that the treatment effect varies across the levels of the other factor. In this case, it's treatment effect varying over gender. So if we have that where the treatment's effective in males, but we see it's different for females, not effective for females, that's a big blow. That's a big blow to any kind of study. And the reason it's a big blow to any kind of study is when you're delivering that treatment, you've lost half the market, right? So again, if we're looking with things with the pandemic, if they found some vaccine that only worked for young people, okay, that's a good vaccine. It's helping one sector of the population, but there's these other, there's the middle, the older that we're losing. So that treatment effectiveness is not universal, right? It depends on sectors of the population, which is not good. Good that there's something for some people, but again, a lot of these effectiveness studies really look at the effectiveness being universal, not conditional. So think about when you guys were in the probability class, the mass stat class, when you talked about conditional probability. Condition, you're in one region of the population, one sector of the population. The treatment effectiveness, you want the treatment effectiveness to be universal, not just focused on one subgroup of the population. In the Dimidian study, one of the things we're interested in was whether or not the treatment effectiveness depended, the treatment outcome, whether or not it depended on race, coded as Caucasian, non-Caucasian, and initial severity, high versus low initial severity. With the 10A work, you guys see some of that down the road. One of the things we were looking at was treatment effectiveness again, but this study was a study of depression. And with the study of depression, these patients were randomized to receive this form of antidepressant or placebo, right? So we had these patients, treatment they were assigned to, medication or placebo. Not everybody adhered to the treatment. Not everybody adhered to the treatment. Some of the people assigned the medication may not take the medication, may throw it away, may forget about it, just are not adhering to the treatment assignment. Similarly, some of the people randomized assigned to placebo might realize they're not getting treated. If they realize they're not getting treated, they might go outside the study to their own doctor or their own psychiatrist and get an antidepressant assigned to them. So in this study with the 10A work, we had a treatment assigned versus a treatment received. And sometimes they'd go hand in hand. People assigned the medication, adhered to the medication, and took it. Sometimes it would contradict. People assigned the placebo, went outside the study and got antidepressant. So when we're looking at the treatment effectiveness, you're trying to say what's happening on average, right? And our predictions are supposed to represent the truth. So when we got this treatment assigned, treatment received disparity where they don't agree, well, that's part of the story. And in these compliance models, a lot of times it'll be called the compliant average causal effect. These CACE, C-A-C-E, compliance average causal effect, and that we start really trying to assess treatment efficacy. And that really becomes a big component, especially in trials that involve some kind of belief that the patients are actually taking the treatment. And that obviously in my line of work with a lot of the psychological studies, that is always subjective and always a worry whether or not this compliance issue, the treatment they're actually receiving, as opposed to what they're randomized to, whether or not that's disturbing or confounding the interpretation of the data. So, but there were a couple of examples where we have two factors, and the focus really is how the one factor is impacting the other's prediction of outcome. So again, the two-way model, the real strength is that interaction, how one factor interacts with the other, or again, in English, how one factor impacts the predictability of the other on outcome. Now, how we attack or how we model that. The book walks you through this initial modeling paradigm, modeling approach. And the modeling approach is called the ANOVA approach. And the ANOVA really says, okay, with these two factors, create one factor that combines the two together. So again, if we were looking at this, we could create one factor that represents each of the 6 cells. So it'd be a factor we call a TX site, where a TX site would be one factor takes on values 1 to 6 or 0 to 5 or whatever you want to call it, that is 6 levels, which identifies one of the 6 possible cells. So again, that becomes something that we could really think about doing in attacking the model. So once you have that one factor, or what I call the ANOVA variable idea, then this really becomes what I call the mathematician's mentality. So all of you who've taken enough math courses have seen this mathematician's mentality in work. And so I'll just show you guys this, little joke here where it says, one day a mathematician decides that he is sick of math. So he walks down to the fire department and announces that he wants to become a fireman. The fire chief says, well, you look like a good guy. I'd be glad to hire you, but first I have to give you a little test. So this becomes the problem for the mathematician. Fire chief takes the mathematician to the alley behind the fire department, which contains a dumpster, a spigot, and a hose. The chief then says, okay, you're walking in the alley and you see the dumpster here is on fire. What do? The mathematician replies, well, I hook up the hose to the spigot, turn the water on, and put out the fire. The chief says, that's great. That's perfect. That's outstanding. You know exactly how to handle this situation. Then the fire chief says, I have to ask you just one more question. What do you do if you're walking down the alley and you see the dumpster's not on fire? The mathematician puzzles over the question for a while and he finally says, I light the dumpster on fire. And the chief yells, what? That's horrible. Why would you light the dumpster on fire? The mathematician replies, well, that way I've reduced the problem to one I've already solved. That's the mathematician's guilty pleasure of analyzing things, turning problems into situations they've already solved. And that's one way to do it. But when we do it in this case, so if we go here and go, okay, the ANOVA approach. The ANOVA approach takes this null and basically goes like this. So I'll take this null and we'll go like this. See if I can get these all together. If I go this way and back up. So in this case, this becomes the null of the ANOVA variable. So the null of the ANOVA approach is this: the equality of the 6 cells. Well, that's, so we know from what we did in the previous section is, okay, the alternative is at least one separating. At least one separating, that's not really what we're trying to get at with the two-way ANOVA model. If one separating with respect to the alternative, that could depend on any of the following 3 stories. It could depend on the effect of level 1 site in this case, the effect of level 2 treatment in this case, or the interaction of the 2. So the AFADA approach here has 6 cells. The AFADA approach here, we lose the testing of the interactive effect. I mean, that's one of the negatives of the one-way approach. The positive, it uses all the data. We're estimating the cell means properly. Now, with the AFADA approach, though, we may get the degrees of freedom are over-specified because we're really, depending the null on the number of cells. The AFADA approach really impacts whether or not the results are generalizable. When we talk about generalizability, that means outside the study in hand, right? Outside the study in hand. So in this case here, with the site gender interaction, okay, well, how do you generalize it to all sites with respect to the treatments? And then the other approach is, how the cells, are being represented in this model. In our AFADA approach model, we're kind of losing the big plus of the two-way ANOVA, and that's namely really getting after the interaction effect. But that's the AFADA approach. So that's one way of doing it. The big thing is, like we said, the big errors of this approach is we get no assessment of the mediation. With the degrees of freedom possibly being off, that means the mean squared error, our estimate of the variance of the within subject variance, will be off. Because again, remember, the mean squared error is the SSE divided by the degrees of freedom. So the degrees of freedom in the error. So if our which is n minus r, when we're thinking r is the number of levels, in the AFADA approach, the whole degrees of freedom could be off. And the big thing is we may also be getting an inflated type 1 error, because if we're trying to dissect what's going on with the components of the AFADA term, we'll have alphas along the way. So we got really, the AFADA approach is a good way to get a sense of what's going on, but we really need to model it as a two-way ANOVA model. So by attacking attacking it in a true two-way model, or even when we build off of this to multiple dimensions, one of the big things that we're really getting after with the bigger components of the model is to really look at that assessment of the interaction. And really, and like so with the multi-factors, well, if we have 5 factors we're possibly looking at. These are all things we want to get after as we get further down the road. And the cool thing with the multi-factors is we want to talk about the multi-dimensions. So interpreting the data as it's intended to be modeled is what we want to do. Again, we want to throw the data we want to model the data, not throw the data into the model. And the big thing is with the multiple factors, we're getting better use out of our model. So that really becomes the biggest focus as we get into. So now, nonetheless, no matter how we model the data, one of the things we need to do is estimate the cell means. Well, estimating the cell means is going to be nothing more than adding up the data within a cell and dividing how many we have. Now in this chapter 19 design, where we have equal number of cells per per observation, that n that n that we saw before in this formation here is so in this case here, that k rather is equal across the cells. Again, in chapter 23, the cell mean is being estimated by the number of observations within the cell. What we're going to see as well is we're going to be interested in getting factor level means. So the mean of, if we go back to the example the mean of all the data within Penn, the mean of all the data within Vanderbilt, the mean of all the data within medication, the mean of all the data within placebo, the mean of all the data within cognitive therapy. So when we're looking at this, we're going to be interested in estimating what I call the cell means, what I call the row mean, the average of all the data across for Penn across the 3 levels of treatment. We're also going to be interested in the column mean as we start, as we start moving forward as well. So again, we're not only going to be interested in the cell means, we're also going to be interested in the column means. So again, row means, column means, cell means, these are all components of the model that we want to estimate. They're going to help us interpret the story behind the model. So it's kind of what we have going on. In this example here, two-way model. In this two-way model, the initial model is fitting what we call a main effects model. In the main effects model, the sole predictors are gender and age. No interaction of gender by age, right? You guys saw interaction terms in the multiple regression class. So the main effects model just focuses on the main effect of gender, the main effect of age. As you see in this table, we see the cell means estimated for this example. We see the column means estimated for this example, and the row means estimated for this example, right? Now, the big thing in this model is there's no interaction modeled. When there's no interaction in the model, if we look at this, the difference in young between men and women is the same as the difference between men and women for middle and men and women for old. With no interaction, the deltas are forced to be the same, not zero, just happens to be zero in that example, but they're forced to be the same, right? So in this case here, no interaction term, the model is forced to have the same amount of difference between any 2 levels of factor A across the levels of factor B. Similarly, you could say it the other way as well. That, for the main effects model, the difference between any 2 levels of factor B within a given level of factor A is the same across all the levels of factor A. It's forced to be that way. It's forced to be that way. So, so the main effects model forces that mathematical construction, that mathematical property of the model. And again, we could see in this case here, for the main gender effect, we could see in this case here, for each level of gender, male or female, we have a deviation from the grand mean for the 2 levels. Similarly, for the age, 3 levels, we have a deviation from the grand mean for each level of age. So each mean response can be obtained by adding the respective gender and age main effect component. So mathematically, the cell mean is equal to the grand mean plus some deviation due to level I of factor A and some deviation for level J of factor B. Right? These deviations are like our tails in the cell in the factor effects model we saw in chapter 17, I believe. So again, those tails. So the alpha betas are really, how in this case, how the main effect component due to factor A gender deviates the grand mean, and how the column effect of age deviates the grand mean. So in the main effects, those 2 components work together to give us the cell mean. So in this case, with no interaction, all treatment means can be expressed in the main effect model layout. Then namely, the cell mean can be written as nothing more than the grand mean plus a deviation component attributable to factor A and a deviation component attributable to factor B. When we, so, and the big thing is, no interaction means that gender does not influence age's impact on outcome, and age does not influence gender's impact on outcome. If we looked at this visually, it means the mean profile plot. And again, we did the mean profile plot for the one-way ANOVA. But for the mean profile plot in this setting, we'd have parallel shapes. So if you look at this example shows a treatment study. This HRSD 17 is a treatment of depression scale. And in this treatment depression scale, patients were randomized to 1 of 3 arms: low dose, medium dose, high dose. And they were additionally randomized to a mode of delivery. So we got a dosage level and what I'm going to call the mode of delivery. In this case here, the mode was flex versus fixed. And what this means is, in the fixed dosage, in the fixed assignment, the patient's dosage was locked through the course of the study. So whatever their dosage level was, it remained the same, within their threshold of whether it was low dose, medium dose, or high dose. In the flex, what happened here is the psychiatrist could increase or decrease within the range of low, within the range of medium, within the range of high, the individual's medication, depending on how they were doing. So this, if they were at 50 milligrams, if they were doing well, they could drop them down to 40 milligrams. If they were doing worse, increase them to 80 milligrams. But the big thing was the dosage had to remain in the low, medium, or high range. In this example, this is showing you the shape of the mean profile plot in a model where there is no interaction between dosage level and mode of delivery. And what you can see here is those 2 lines are the same. And if we start looking at the differences, so the difference flex to fix, 4 units that go in 14 to 10 for low dose, right? If we go here, this is, so again, 14 to 10. This is going 14 to 10, right? So in this case here, this is probably 22 to 18, 4 units difference. And then we go here, this is probably, probably what, 14 and a half, 18 and a half. What you see in this case here with no interaction, this difference, 4 units, 18 and a half to 14 and a half, right? 22 to 18, 14 to 10, that difference remained the same. So the on average difference flex to fix is the same across low, medium, high. That means there's no interaction in the model at all. So that means the impact of, the low, medium, high dose impact on outcome, is not differential as a function of mode of delivery, right? If you think about it, the flex fix, that just has an attenuation, right? If your flex, regardless of dosage, it just shifts it up 4 units on average. And then similarly, if you're fixed, you shift down, right? Now, as you guys can see here, if I'm looking at this in terms of the main effects model, in this model here, in this mean profile plot, this is saying to me there's a main effect of dosage type. Of mode of delivery rather. Because again, flex on average is higher than fixed for each of the 3 dosage, right? That's a main effect of mode of delivery. Additionally, if you look at dosage level, so if you disregard the type of delivery, the average for low dose is probably right here. The average for medium dose is right here, and the average for high dose is right there. Those 3 averages as a function of dosage amount are not the same. So this would say to me, I have a main effect for dosage type, a main effect of mode of delivery, but no interaction, right? So again, the on average difference between flex and fix remains the same across the 3 levels of dosage amount. You could also graph it flipping what's on the x-axis. In this case, we have the mode of delivery on the x-axis and the lines being represented by dosage amount. And in this no interaction model, you could see the lines are running parallel, right? There's no interaction in this data. Well, we want to see that there is no interaction. And again, that means the difference between mean responses for any 2 levels of factor B remains the same for all levels of factor A. And again, you word it the other way as well. The difference between mean response for any 2 levels of factor A is the same for all levels of factor B. The big thing is these curves are parallel, as you see there. If our mean profile plot looks like that, that's an interaction. That's an interaction. So when I'm trying to determine which, and we'll word it this way, which treatment delivery type, flex or fix, does better, and remember, lower is better. Lower the score better. Which mode of delivery does better depends on the dosage amount, right? When we're at low dosage, on average, fix is better. Results in an on average lower HRSD 17 score. Where medium dosage, the flex is better compared to fix. It results in a, on average lower depression score than the fixed dosage. And then similarly, when we're at the high dose, the fixed dosage is better. So now if you think about it, in these ones, the on average difference is 4. The on average difference is 4 units. The on average difference here is 4 units. But the 4 units aren't in the same direction, right? This is flex above fixed. So doing flex minus fix, this delta is 4. Flex minus fix, this delta is -4. Flex minus fix, this delta is 4. So if we go back to this, in this case here, the on average differences are not the same. Right, we go 4, -4, 4. So again, whether or not those differences are substantial enough would end up, indicating enough evidence or data to indicate that there is truly a significant interaction in this case between dosage mode, treatment mode, flex or fix, compared to dosage amount, low, medium, high. So that has an interaction. Interactions can be detected when the mean profile plots cross like this. And you can see again that mean profile plot crossing as we observe it. In this model, when we have an interaction model, we need to estimate an additional term which represents how the cell mean for level I of factor A, level J of factor B, how that differs from the grand mean, as we start moving on. Namely, the big thing is that the cell mean needs to have that additional interactive term in its layout for us to estimate what's going on, to estimate the cell mean. So that's really what we need to go after as we move on here. So we need to get that additional component to estimate the cell mean, the component I'm going to call the interactive component. So recognizing of the interaction, model-wise, we need the cell mean to include the interaction component, because the cell mean, the additive component doesn't get it. The big thing in terms of English is the difference between the delta, difference between A pairs within a factor, consistent across the levels of the other factor. The answer is no, we have an interaction. And the big thing is, look at the cell plot. Now, are the cell mean plots running parallel, or are they not? If they're not, there is a possibility you have an interaction term in the model. Another area of the book where the book and I kind of differ is the book talks about looking at things called interactive, or called unimportant interactions. And in a mean profile plot like this, in this layout here, the book may call this an unimportant interaction. And sometimes the book will say, well, use a transformation to remove the interaction. I don't agree with that. Right? If the interaction's there, it's part of your story. And like I said to you guys before, from an analysis perspective, from an analyst perspective, statistics is communicating the story of the model, right? We transform the data for a lack of fit of the model, not for getting away, not for hiding part of the story of the model. In this case here, this could be an interaction. And the reason this could be an interaction is because the on average difference between flex and fix does not appear to be the same as we go across the levels of dosage, right? So in this case, flex versus fix, that's 4 units there for low dosage. For high dosage, it's 18 to 12. That's 6 units of difference. And then when we get to the high dosage, that's 18 to 15, that's 3. So if we look at the deltas, it's 4. I'm going to say flex minus fix, +4, +6, +3. This could be an interaction. We saw this as an interaction. This interaction you're seeing right here, I would call this a disordinal interaction. And the reason I call it disordinal, D-I-S-O-R-D-I-N-A-L, disordinal, is because the on average difference between flex and fixed is not the same across the 3 levels of dosage. But not only that, it's disordinal because the difference flips direction as we go across the different levels, right? This is a positive. This is a positive. This is a negative. That flip of direction is what we call a disordinal interaction. Disordinal interactions are recognized when the mean profile plots like this cross. That's what we call a disordinal interaction. That crossing is representative of a disordinal interaction. This I would call an ordinal, O-R-D-I-N-A-L, ordinal interaction. And the reason I call this an ordinal interaction is because the deltas are not the same. The on average difference flex to fix is not the same, right? It's 4, 6, 3. They're not the same, but the differences are in the same order. They have the same magnitude. The mean profile plot does not cross, right? So the on average differences are the same, but they're varying in magnitude. So again, remember with the interaction component, it's this null. Know that the on average difference between 2 levels of factor A are the same across the levels of factor B. In this case here, in this visual, we know they're not, but they're in the same direction. So this is what I would call an ordinal interaction. And whether or not something's an interaction or not depends on whether or not it's a statistically significant interaction. So that becomes one of the big components. So again, going to the book, the book says, oh, if the interaction's unimportant, transform it away. Now that's hiding, right? That's hiding. So the book would say, we say that interactions that are present act multiplicatively, if I could talk, can be removed by considering a log transformation. I just don't like that. I don't like that. So when these interactions cannot be removed by transformations, the book calls them non-transformable interactions. But the big thing is watch what that interaction does to 2 things. Does to your model fit. Like we said in chapter 18, when you're doing something to the model, the question becomes whether or not you're breaking something in the model. So with the transformations, you could correct something, but impact the homoscedasticity, or in our case, the homogeneity of the variance. You can affect the normality of the residuals. So you've really got to be worried about it. I don't like this transformable interaction term. That's why I got the to me, it doesn't make sense. If the interaction's there, it's part of the story, and it's part of your storytelling. Again, I'll say this throughout the course, and if you guys have me in future courses. Statistician's job is communication. It's not mathematics, right? Transforming is mathematics. We're telling the story of the data, right? And to tell the story of the data, if the interaction's a component of it, like it is here, that's interaction. Namely in this one, the big story here is, for whatever reason, the biggest difference between flex and fix is observed at the medium dosage. At the high dosage, we see that difference becomes less, as well as the low dosage. So why is the impact of leaving it at the hand of the psychiatrist to decrease the dosage? Why is it more, in this case, lower is worse? Why is there a bigger difference in outcome between the fix and the flex for those medium dosage people? Right, so that could be part of the story. It's not a story. It's not a part of the story that we be privy to the resolution of the story. No, we're showing the investigator the data. They may be going, okay, well, why is this exaggerated? What's going on with those individuals? What causes that? And that becomes, part of the clinical story. And it's an important component of the story. especially when people start looking at combining medications, delivering the medications. So how things impact for the worse or for the better is really part of the story of what we got going on. Here's this graph here. This graph here, I think, gives the layout of all the possible interaction mean profiles you could see. So the one graph I showed you guys the first class was created by my friend Shin Tu, who is a professor at the University of Rochester. I think he's visiting in San Diego now. But he teaches a similar class at University of Rochester. This is 513. And he showed me this graph. I thought it was pretty cool. And that's why I'm sharing it with you. In this example here, we have two factors, one called region and one called gender. And as you guys will notice, is the region is on the x-axis. And region's on the x-axis, and the colors indicate blue for men, red for women. And we're trying to assess this impact on the outcome, whatever the outcome is in this case. So you guys see the regions are 3, east, west, south. The gender is men, women. I asked into what happened to the, what happened to the north, and he goes, Bob, I do not know. And so since he doesn't know, I do not know. But there's no north here. So we got the east, west, south. If you look at the first example here, when I see this mean profile, this says to me that there's no effect due to region. And again, if you look, so if you look at the overall mean for the east, so averaging between the men and women, they're right on top of each other. It's right there. The overall mean for the west, right there. The overall mean for the south, they're exactly the same, right? So no effect due to region. There's also no effect due to gender. And the reason for that is that there's no effect due to gender. You can see that the means are right on top of each other. The red and blue lines are right on top of each other. Now, additionally, there's no interaction because the on average difference between men and women, which is 0, is 0 for each of the 3 regions. So this mean profile plot indicates no main effect due to region, no main effect due to gender, and no interaction. This mean profile plot right here, the upper right corner, this looks like what we just saw with the flex fix first example, or maybe it was the age, the age gender example. But as you guys can see here, this says to me that there's an effect due to region, right? So again, to get the main effective region, we look at the average between men and women, per region. So the average within the east is right there. The average in the west is right there. The average in the south is right there. Those 3 means are not the same. So that's saying to me there's a main effect due to region. Now, if you look at the gender effect, as you can see here is, the red and the blue are not on top of each other, right? So when I look at this, if I want the average for men, or women rather, women are the red, the average for women across the 3 regions, probably right about there, right? Probably right about there, as you see. So if you average the men across 3 regions, that's probably right around there. So that delta, that difference remains the same as we go over the levels of the region. So that on average difference is the same. So we have a main effect due to gender. But in this one, the on average difference between men and women remains the same across the 3 regions. That's no interaction. So this mean profile plot has a main effective region, main effective gender, but no interaction. Go here to this next one. So right away, you see the blue and the red line are not on top of each other. So that's a main effect due to gender, right? But when we look at region, the mean for the east, averaging between men and women, is right there. The mean for the west, right there. the mean for the South right there. Those three means are exactly the same. So there's no effect due to region. Now look at the deltas. The difference between men and women, difference between men and women, the difference between men and women. Those three deltas are exactly the same. So we have no interaction. No, the lines are parallel. If we go here, you can see the blue and the red are right on top of each other. So again, we have no effect due to gender. But if you look at the region, here's the main effect due to men. Due to the East, due to the West, due to the South. Those three means are not the same. So the main effect of region. But the difference between men and women is zero, nearly zero, across the three regions. So we have no interaction. The last two are our interaction mean profiles. This one here is what we call an ordinal interaction. This one here, we call a disordinal interaction. The lines cross. So now if we focus on this, here's the men in blue. So the average for the men across the three regions is probably like right around here. Right around here. The average for across three regions for the women is right about there. So the main effect of gender is significant. And we see the red and blue are not on top of each other. So there's your main effect due to, your main effect due to gender. When you look at the regions, right, here's the mean for the East, right between those two dots. The mean for the West between those two dots, and the mean for the South between those two dots. So these two means are higher than that mean. So that means there's a main effect due to region. But now look at the differences between men and women across the three regions. Small, small, boom, big, right? The difference between men and women minus men, positive. Women minus men, positive. Women minus men, big positive. That's an ordinal interaction. The on average differences are in the same direction, but vary in magnitude. That's an ordinal interaction. If we go here, the lines cross. That's what we call a disordinal interaction. And now, if you look at this, if we want to look at the regions, now the mean in the East is basically the average of these two cells, which is right about there. The West, the average is right there. And then the South, the average is right there. Those three averages are the same. So I see no main effect due to region when I'm collapsing across gender. So do the same thing with gender. The mean for the women, here's one cell mean, the other cell mean, the other cell mean. The mean for women's right there. Same thing for men. The mean, the mean, the mean. The average of these three data points for the men is right there. So the on average mean for men and women aren't different. So no effect of gender, but the interaction is there. And this is a disorder interaction. Women minus men, positive. Women minus men, 0. Women minus men, negative. Right? So we see positive, 0, negative. So the on average difference is not the same. And not only varies in magnitude, but direction. That becomes the disorder interaction that we see here. So when we get here, part of our thing here is to really get at, to get after, estimating the cell means, get cell means, deviations in the mean. So we're getting at the mathematical formation of the model. The on average mean per items within a cell is that cell mean. The variance is right there. And then model-based assumptions are the data. The data are distributed normally with mean equal to the cell mean and some common variance. So in this case here, we could be looking at, if we have 2 observations per cell, as we start moving down the data, we get the cell means and the deviations in the cell matrix, in the vector matrix layout. Nonetheless, we're really interested in getting the cell means as we move forward. So for the factor effects model, the big thing is for us in the interaction layout, the cell mean can be written as the overall mean or grand mean, a main effect component for B, and an interactive component. So with the factor effects model, SAS is going to go ahead and estimate these through the raw data. And so the cell mean, like we just said, all depends on the grand mean, an adjustment level for factor I level B, an adjustment level for factor J, level J of factor B, and an interactive component. So it's an additional adjustment that takes into account both level I of factor A and level J of factor B. Whenever we're running these models, a couple of things that we're going to see is that these respective coefficients, the alpha terms, the beta terms, and the alpha beta terms, they sum to 0. We saw that with the tau terms. The alphas sum to 0, the betas sum to 0, and the alpha betas, whether or not we hold a level of factor B constant or a level of factor A constant, the alpha beta components sum to 0. They're basically your deviations, and we know deviations sum to 0. So again, as we sum over the alphas, they will sum to 0, and same thing with the betas and the alpha beta terms. So now let's take a look at this example here, chapter 19, 833. So if we go to the textbook, chapter 19, 833. So keep going. Went too far. So right here. So in this case here, we have the Castle Bakery Company supplies wrapped Italian bread to a large number of supermarkets in the metropolitan area. Experimental study was made to assess the effect of height in the shelf display, right, which is bottom, middle, top, and the width of display, regular versus wide, how that affects the sales of cases. So it's almost kind of like the Kenton data. So we got a shelf, we got a shelf display, bottom, middle, top, and we got a shelf width, regular, wide, and how this impacts the effect on the effect on cases sold. So we got this here. So I'm going to pull up this program really quick. So we're in 1983. So I have to go to you guys, WCU laptop, go to STA 513, go to slide program. So in this case here, and again, if you guys remember, I'm going to put the num on, put the number lines on the side. Kind of like what we did with the one-way ANOVA. We're just going to run the model. We're going to run the model and take a look at what we got here. So in this case, remember line 4, that's just about the HTML out. It helps lay out what the SAS output window creates. I'm going to load the data. I'm going to print it out. Right, so again, we got our 3 heights, low, middle, high, and we got our widths, regular, wide, regular, wide, regular, wide. Get 2 observations per cell. So in this case here, we're going to just run the model. So in the two-way ANOVA, the big thing we want in the model statement is the main effect of the first variable, the main effect of the second variable, and the interaction. Now, if you guys notice on line 31 and 32, I'm using either the mean statement or the Ellis mean statement to get the cell means. I kind of like doing the Ellis mean statement preferably, but again, it's up to you. Let's just run the model and we'll take a look at what's going on. Here comes the model. Right, here comes the layout. I'll go to the top of the output. Right, so now we get to the model. Right, so 3 levels of height, 2 levels of width. We get the overall model, 65 degrees of freedom used for the model, 6 for the error, 11 left over. So again, remember our correct total is n minus 1, n total minus 1. 0.0003. Now, the p-value we see there doesn't tell us anything about the ANOVA model. You know, like with the multiple regression model, this is saying us, based on the available data, at least one term is significantly associated with the outcome. Right, that's all that's saying to us. We all know it's the main effect of height, the main effect of width, or the interaction component. We all know that. We all know that. So again, we got more of the output, but now we got the type 1 sums of squares and the type 3 sums of squares. So now, remember the type 1 sums of squares. They indicate the significance of the respective term adjusted for the variables that preceded it. That's height. That's width adjusted for height. That's height width adjusted for the 2 main effects. But when you guys look at this, you see the type 1 sums of squares and the type 3 sums of squares are exactly the same in this layout. The only reason that happens in this case is that we have equal cell size. When we have equal cell size, that creates what we call an orthogonal design. And when we have the orthogonal design, the type 1 sums of squares and the type 3 sums of squares will match. Usually I don't have orthogonal, I'll have equal cell size. So, you know, they do not match when you don't have that orthogonality. For me, my attention always goes to the type 3 sums of squares because again, it's the significance of the term adjusted for all the other terms in the model. And in reality, in the two-way ANOVA, my attention goes immediately to the highest order term, the height by width interaction. So with this height by width interaction, this is saying to me, based on the available data, I do not have sufficient evidence indicate that the on average cases sold, the on average difference in cases sold between wide and regular width shelves varies differentially across the low, middle, and high displays. Right, so I do not have that evidence. So now in this situation, when I'm fitting this model, remember all the models go to parsimony. So I would take that term out of the model, right? The interaction is no longer significant. So that term would go out of the model and I would create a parsimonious model. Now, what I would do is in these kind of models, especially when we move forward, we have unequal cell size, the model simplicity should be one step at a time. So in a normal situation, I would look at this model and I would take the interaction out of the model and rerun the model. Now, in this rerun in the model, I would know based on the type 1 sum of squares, width is not significant. So in reality, the model we have should reduce to just a main effect attributable to height. So this overall p-value you see there, that was really telling us that we have at least one term significantly associated with the outcome, and that one term we see here is height. So namely, on average, the cases sold vary differentially across the 3 levels of height, regardless of the width of the display. In SAS, it's going to create this mean profile plot. This is pretty cool. It's a pretty cool mean profile plot because it's showing us the height on the x-axis, the width on the y-axis. So when you look at this mean profile plot, and we're going to show how to do it ourselves with the SG plot component of the data, but this does a really nice job of creating this mean profile plot. When I look at this mean profile plot, the one thing I notice for the most part the red's above the blue. Now, obviously, it's not here, but man, yeah, I'm beginning to wonder: do I got a main effect due to the width? This probably eliminates it. I see right away that regardless of width, so if I collapse across the width, here's the average of the data right here for the low height. Here's the average for the high height. I could see on average, the most cases sold corresponds to those individuals at the high height. This is showing me the main effect attributable to height. Now I start focusing on the interaction. I see the mean profile plot crosses. So now with that cross, I'm thinking disorder interaction. And now with this layout, I look at the on average difference, wide to regular, wide to regular, wide to regular. Those on average differences don't appear to be the same, right? But again, our null, the on average difference between low and high, wide and regular, does that vary differentially across the three heights? Even though the mean profile plot crosses, there is just too much variability in the data to yield a significant interaction. So we do not have a significant interaction. That is, based on available data, we do not have sufficient evidence to indicate the on average difference between regular and wide varies differentially across low, mid, and high displays on average. So again, we keep that in mind as we move forward. So this is from the two-way model. This starts giving us box plots for the main effect. So this is coming out from our means command for height, width, and the interaction. So right here, this shows me the main effect due to height. Again, we see the on average sales there. This is the width. Again, it doesn't appear to be on average difference with respect to width. And then this is the two-way ANOVA layout from the mean statement. In this case, it's not giving me this nice plot. This plot is the plot we need to do to assess interactions. This plot you guys here is basically the AFADA plot. We have on the x-axis the combined height, width as one factor. So while I see these two cells shift up, based on this plot, I don't know if what's driving that difference in the 6-cell means is being driven by the effect of height, the effect of width, or the interaction. From what we just did above, we know these two, which happen to correspond to height level 2, these two separating from the pack is really attributable to the height main effect. No effect due to width and no interaction effect. Again, that gives us the respective means. This is the output for the Ellis means. Again, this one's going to give me just the mean profiles for the two. Again, pay attention to our y-axis and then that mean profile plot. But we just ran that, just running the model blindly, right? Well, one of the things we saw in one way is what we need to check some of the model diagnostics. On line 38, it would seem I should be able to lay out the homogeneity of variance test like we did for one-way ANOVA. So right there on line 38, I threw out the option HOV test. So let's go ahead and run the model. Now, pay attention to what the log was saying to me. Now, the log is saying that homogeneity of variance testing and Welch's ANOVA are only available for unweighted one-way ANOVA. So in this case here, I don't have the ability to test homogeneity of variance. No, so namely in this case, homogeneity of variance, right? So when we start going to, model building, for us, HOV means equal variance across all the cells. That's what homogeneity of variance means for us. Because again, if we go back to our PowerPoint slides, we're assuming the Yijk rather, have constant variance across every cell. Homogeneity variance means that now. Now that every cell has equal variance, right? So if we get back to where we were, in this case, we're not able to assess that with this command. So how are we going to test homogeneity of variance? How we're going to test homogeneity of variance is we're going to create the ANOVA variable. And what you see here on line 45 to 50, I'm creating a variable, HW, which combines the level of height and the level of width, right? So what you guys can see is I'm numbering the 6 cells. So this one right there is telling me I'm on the bottom regular display, bottom wide display, mid regular, mid wide, top regular, top wide. So I'm going to run this. So I load that variable. In this portion right here, what do you guys see me doing here is now I'm basically running the ANOVA analysis. The ANOVA analysis, the mathematician's guilty pleasure, is to turn the two-way model into a one-way model with the ANOVA variable. In this portion of code, with that ANOVA variable, I'm able to throw that ANOVA variable into line 56. And in line 56, I'm able to ask for the homogeneity of variance test. This block of code, I'm going to not use that output at all except for the homogeneity of variance test. So when I run this, this gets me to the homogeneity of variance test right there. So some of you guys say, well, there ain't no output, right? And in this case here, there's no output for this homogeneity of variance test because the cell sizes are 2. So for Levine's test of homogeneity of variance, we need more than 2 observations per cell, or it won't estimate. But mainly, if I was trying to assess homogeneity of variance, I would 2 steps. Create the ANOVA variable, the variable that combines the 2 factors of interest. Second, run the one-way ANOVA with the ANOVA variable. Ignore all the output except the output being generated by Levine's test in the one-way ANOVA of the ANOVA variable. So if I go here real quick, I'll show you guys how to get a little of the how to create a little of some of the plots, right? So this one is using the ANOVA variable to show the data. Kind of nothing really different than the box plots we looked at. Here, this one's creating the mean profile plot with G-plot. But like we saw before, again, you guys can let ProcGLM create that two-way plot for you. Here I'm showing you some of the template for creating the mean profile plot ourselves. This is SG plot with the mean profile plot, connecting the dots, connecting the raw data or displaying the raw data. Overlaid with the ANOVA variable. Here I'm creating the overlay of the two plots, but I think this is the better of the two. Right, so once we create that data here, doing it like this with the SG plot creates the ANOVA plot. Creates the two-way mean profile plot ourselves. So the big thing in creating this plot, again, the big things with this are namely, the big thing with this are to get the cell means. With the cell means, get the cell means back into the original data, which we're doing right there. And then here, the SG plot we just looked at, this one here, actually this one here, line 178, gave us the best overlay plot that we want. So again, keep that in mind as we move forward. Here, if we go here real quick, give you guys just a couple more outputs. If I do the solution option on the output, let me show you guys what happens here. So this is showing us our regression coefficients, right? So in this case here, level 3 of height's the reference cell for height. Width 2 is the reference cell for width. Right, so the 44, like what we saw one way in ANOVA, that represents the cell mean for height 3, width 2. Then this represents the deviations attributable to the main effect of height, the deviations from the reference cell due to the main effect of width, and then these are the deviations attributable to the interactive component. So again, you could think of these as those as the alpha parameters, these as the betas, then these as the alpha betas. Keep in mind too, the ordering of the variables is focused here. Height, width. Height first, width. So height, width. In this interactive component, keep in mind the notation. As we go down these parameters, these are showing you the deviations. The first one, height 1, width 1. Height 1, width 2. Height 2, width 1. Height 2, width 2. Height 3, width 1. Height 3, width 2. So the deviations have width iterating within height. So again, something we just have to keep in mind as we move forward. If you throw the auto plots into the mix, go all the way to the top of the output. I think this is our output. All right, so the auto plots, the predicted values is a function of the residuals. Now, if we look at this standardized residuals, it doesn't look like there's any outliers here. No issues with respect to leverage. Normal probability plot makes us wonder about normality. The Cook's distance, nothing seems to be a problem there. Now, the residuals look a little, not exactly normal. Obviously, we test that Here's our mean profile plot. Again, a couple of things we saw in one-way ANOVA, but I'm going to take you guys down to here. Here's the Ellis mean tables, and this is showing us all the pairwise differences. So the big thing is you got to keep in mind what you're comparing. So this is 2 to 5. 2 to 5. So that one I've highlighted is quantifying the p-value and testing the equality for bottom wide, that's height 1 with 2, to top regular, that's 3-1. Right? That's 3-1. So it's 43 versus 40. Right? So based on available data, we do not have sufficient evidence to indicate a significant on average difference in sales for the bottom wide display compared to the top regular display. Right? And that comes with a p-value 0.39. If we round it to 2 decimals. If you go here, the 6.4 is 3.2, that's 6, compared to 2.2. Right? So we can see that based on the available data, we find sufficient evidence to indicate that the on average sales is significantly different between 3.2, so the top wide, which yields 44 cases sold on average, to the middle wide, which indicates 69 cases sold on average. So that's why that's highly significant. So again, with the pairwise differences, you need to use this Ellis mean number to keep yourself situated on where you are in the box below. And then similarly for the confidence interval differences, like this 1.5 you guys see here, the Ellis mean difference is 5. So the 1.5, we know is a p-value 0.178. The 1.5 is looking at bottom regular compared to top regular. So we see our 45 to 40, we see that on average, bottom regular has 5 cases more sold on average than top regular. We're 95% confident the true average difference in cases sold ranges to as much as 12.8 more cases sold for bottom regular compared to top regular, to at worst 2.86 cases sold more for top regular compared to bottom regular. The big thing with that confidence interval, it contains 0. So this doesn't tell us anything about whether or not there's a significant difference, on average difference, between the levels. If I show you guys this real quick, this line 204, I added an extra line of data on line 217, right? Or my fault, not line 217, line 213 is where I added the extra line of data. When I do this, I'm just going to run these two together. With the extra line of data, trying to see what happened there. So we got 1-1, 1-2, 2-1. We got 2-1, 2-2, 3-2. So if you guys notice here, we lost the 3 1s, right? There's no 3 1s. So if you guys notice here, we have 3 levels for height, 2 levels for width, right? So namely, we got the height 2, the width 1. If you remember with the previous output, when we looked at that, We want to drop all the way up to that. In our original model, we had 2 degrees of freedom for height because of the 3 levels, 1 for width. The interaction was 2 times 1, which is 2 there. If we drop down to where we were, so when you guys look at this, what should really happen in an interaction model is the degrees of freedom for the main effective height, the degrees of freedom for width. So the degrees of freedom for the 2 main effects terms, their product should equal the degrees of freedom for the interaction term. So really, the degrees of freedom for the interaction term should be 2 times 1. When it's not, that, and this is where you gotta pay attention to the output, that means there's an empty cell. One of the cells is missing. And as we see in the mean profile plot, we're missing the 3-1 group. We're missing the 3-1 group. So again, keep in mind, as an FYI, when the degrees of freedom for the interaction component is not the product of the degrees of freedom for the main effect terms that comprise it, that usually means there's an empty cell, something's missing. So to keep that in mind, this one's going back to our original data. So right on line 233, I'm kicking out the residuals. And with the residuals, I'm just going to go ahead and plot manually the normal probability plot. So again, when you guys see the normal probability plot, it's not linear, right? So I'm beginning to wonder whether or not the residuals possibly aren't normally distributed. Again, that's a visual. We said the best way around the visuals are to look at the normality test. So when I look at the normality test, here's the normality test of the residuals, right? So you could see now, if we focus on the 2 big ones, the Shapiro-Wilks and Kawamura-Smirnov, we can see based on the available data, we have sufficient evidence in our data to indicate a significant deviation in normality for the residuals based on the Shapiro-Wilks. Therefore, we have violated the assumptions of the model, namely the violation of normality of the residuals. If your data analysis plan said use the Kawamura-Smirnov, then you'd have no evidence, not sufficient evidence to indicate a deviation in normality. So this is kind of a little bit of a quagmire. For me, I would look at this as evidence of a deviation in normality. I would turn to the Box-Cox transformations here. So Proc transreg would be something we would consider in that case. If you guys see here, I'm changing the confidence intervals to 99% with this code. So again, you can see everything's 99% as we move on. If you guys notice here, line 279, when we start looking at the LS means, we can again do the adjustments. On line 279, I'm asking SAS to do the Chaffee adjustment. So when I go here and run this block of code, I'll go up to the top, right? So this is looking at the interaction and showing us multiple comparisons are Chaffee adjusted. Therefore, all pairwise comparisons here have an overall alpha level of 0.05. So in making all, in this case, it's 6 choose 2, right, which is all 15 pairwise comparisons, the overall alpha level is 0.05. Or do we do 0.01 in this case? 0.01, right? So we have all the comparisons Chaffee adjusted in this case. So again, we just go right there with the Chaffee adjustment. So again, we're right here, back at the data. So I'll load the original data back up, 12 observations, right? So again, you could do the just equal Tukey, the just equal Chaffee, the just equal Bond, right? So no matter how we do it, it's giving us the overall, overall comparisons are adjusted, the overall alpha level based on the comparisons is adjusted through one of the three techniques. Again, it's just throwing the adjust into the respective Ellis means line. CL-PARM will give us confidence intervals for the regression coefficients being estimated by the model. And remember, it's going to do that for both that and the estimate statements. So let me get back to PowerPoint slides, right? So we fit the generic notation. We applied it to the Castle data. The big thing is, our ANOVA model goes to fitting this equation. So the least squares is minimizing this equation, which for us is really how the observed data value deviates from the estimated value, which again, the estimated value is depending on the grand mean, deviation due to level I of factor A, level J of factor B, and the respective interactive component. Remember, we said with the alpha betas, the alpha beta parameters will sum to 0. The alpha betas will sum if we hold J fixed across levels of I, they sum to 0. If we hold J fixed across levels I, they sum to 0. So again, the whole model is being estimated as a function of the respective means for the respective cells. Big thing is EIJK, the residual is nothing more than the observed data value minus the predicted, which is the cell mean. We just looked at this predicted versus observed in SAS. Whoops, I just went to the end, my fault. Did not mean to do that. Where we were just at, so my apologies for jumping. Again, the sums of squares are going to depend about deviations around the cell mean for the observed data values and the deviations of the cell means from the grand mean. So again, we have a component due to the model, which we call sum squares due to treatment, and the sums of squares due to the error. I just did that again. I keep hitting end instead of page down. My apologies for making you guys dizzy as I do this. So now for us, the sums of squares of the model can be broken down into these three components. A component attributable to the main effective A, main effective B, and AB. So the sum of squares attributable to AB is the sum of squares of the model minus the sum of squares of two main effects components. So the sums of squares total, the two main effect components, interaction component, and the sum of squares error. So the degrees of freedom without empty cells should follow this pattern. Degrees of freedom for factor A, the number of levels of factor A minus 1. Degrees of freedom for factor B, number of levels of factor B minus 1. Degrees of freedom for the error should be the number of levels of factor A times the number of levels of factor B times the number of observations minus 1. And then the degrees of freedom total is n minus 1. When the data do not comply to these rules, then that's usually an indication you have an empty cell, as we just saw in the previous example. So the mean squares are just those sums of squares divided by their respective degrees of freedom. And then the big thing is the expected value of the mean squared error estimates the pooled variance, sigma squared. So again, if we go back to 833, and we look at the main model, I'll get to the top. I'm not at the top. Here I'm at the top. Right, so with our sums of squares, right, remember height's 3 levels, 2 degrees of freedom. Width's 2 levels, 1 degree of freedom. Height width, that's 2 times 1 is that degrees of freedom. Right, so again, our mean squares are these sums of squares divided by their respective degrees of freedom. Then we start getting that with our mean squares, then respective F values. So again, our total degrees of freedom, 2, 1, 2, are the number of values in the model. So to keep that in mind, again, if you look at these sums of squares, right, so the 1544 plus 12 is 1556. 1556 plus 24 is 1580. So again, the sums of squares sum. It's why they're sums of squares. As we keep moving on, so the big thing is, with respect to model checking, what we learned in chapter 28, or chapter 17 and 18 rather, carry over here, namely normality, which we just saw an issue with normality when we used the Shapiro-Wilks homogeneity variance, which in this data we run into a problem considering there's only 2 observations per cell, and then whether or not we have independence of the error term. That's where the autocorrelation effect could come into play. So for the two-way ANOVA, we could test the main effective factor A, the main effective factor B, and mostly the interaction. So again, if we go back to the output, this is assessing the main effective factor A, the main effective factor B, and the interaction. Right, so this is doing all these hypotheses. So again, based on available data, we can see that on average, the cases sold is not the same across the 3 levels of height, regardless of width, and that on average, at least one of the heights yields significantly higher sales, significantly different sales compared to the others. Do not see an effect due to width, and we do not see that the on average difference in width on outcome varies differentially across the 3 heights. So that's all we're saying from that. Again, all the tests just go to those F statistics. Again, the ANOVA table, SAS is doing all the work for us. And then the book starts looking at, I guess, almost the multiple comparison idea. And namely, with Kimball's inequality, they talk about alpha 1 being the level of significance for factor A, alpha 2 for factor B, and alpha 3 for the interaction. So Kimball's inequality uses the fact that while the numerators are independent and denominators are not, therefore the true alpha rate in assessing the main effect components and the interaction component has this quantity. That's true. That's getting at kind of multiple comparisons for looking at all components of the two-way ANOVA. But I say this to you guys. When I look at a two-way ANOVA, my main focus is on this interaction term, right? So all my alphas go into that, and namely, if the interaction's not significant, we therefore have no evidence in our data indicate that the on average difference in sales across wide and regular widths vary differentially across the 3 heights. So I used all my alpha to protect my type 1 error in that assessment. Once I'm done with that, then I'm going to fit a new model that removes the interaction. If that interaction's significant, in reality, you don't really care about the main effects. Now, if the interaction's significant, what's the story behind the interaction? Is it an ordinal interaction? Is it a disorder interaction? Where do we see the impacts happening? Right? So, the Kimball's inequality, again, another issue where the book and I aren't exactly in alignment, is that while it's a true statement, what they derive as far as getting after the alpha rate, it's not really something we really want to focus on. We really want to get after that interaction. So anytime we run a model, our big strategy is to run the big model, right? If the interaction's not significant, then drop it and fit the main effects component. If they do interact, then our big thing is the interpretation of the interaction. And what does that mean clinically? Now, the clinical importance, we don't answer. It's the person whose data it is answers that question of whether or not the interactive behavior we see is significant or not. So that really becomes what we really start getting after. So however we attack this, we can get confidence intervals for these terms and all that. And not only with confidence intervals for the main effect components in the interaction that we saw right here with this command, right? When I go here, not right there. When I go here, line 279, I'm asking for confidence limits with the CL command there. Confidence limits adjusted for the Scheffé adjustment for the main effect height, the main effect width, and the interaction. And we saw this creates a lot of output. A lot of output. Right? So here's my confidence limits for the differences between A and the 6 cells. Confidence limits for the 6 cell estimates, Scheffé adjusted. The confidence limit for the respective cells means for the 2 levels of width and the difference. And the same thing for the 3 levels of height. So the 3 levels of height, their confidence limits, and the on average difference and the confidence limits. And these are all Scheffé adjusted. If we don't want the Scheffé adjustment, just get rid of the just equal component and not have it there. They'll be unadjusted. So we just saw that we can use SAS to do all this derivation for us. But now the big thing is, how can we use SAS to do contrast? To do contrast and power. So we're at slide 56, and we'll pick this up in the next video. So as you guys see here, this was, video 6. So when we go to video 5, video 7, next we're going to look at contrast for the 2A ANOVA model and power, and possibly go into chapter 20. So that is the next topic we do as we move forward. So this is the end of video 6. Thank you for your participation, and I'll see you in video 7 shortly.